All right, so welcome everybody to another edition of the Heidelberg Joint Astronomical Colloquium. And this week we're switching topics to radioastronomy. We've not heard a lot about radioastronomy, at least not if you don't count ALMA as a real radio telescope. But this time we're going into the real red-blooded radioastronomy regime, longer wavelengths. And I think it's fair to say that this is an area which is experiencing a rebirth, even a revolution. And we're extremely happy that today we've got Michael Kramer to tell us a little bit about some of what you can do with this in the area of fundamental physics. Michael Kramer's host is Friedrich Rueper, and I'll ask Friedrich to formally introduce Michael.
Yes, it's my pleasure. So Michael is from Cologne and graduated from Bonn and Cologne and got his PhD in 1995 from Bonn, and then joined the Max Planck Institute for Radioastronomy as a staff astronomer, and with a Otto Hahn fellowship, then moved to UC Berkeley in 1998, and then afterwards returned to Europe, to the UK, where he then climbed the ladder of tenure track at the University of Manchester. And he's also been the head of the Pulsar group at Jodrell Bank Observatory, and also later became associate director there. Since 2009, Michael is director at the Max Planck Institute for Radioastronomy in Bonn, and he is, as Richard already said, known for his work on pulsars, and in particular also the application of pulsar astronomy to test the theory of gravity. Michael has received numerous prizes and awards. Just to name some: the Marcel Grossman Award, the Herschel Medal, and in 2016 he gave the prestigious George Darwin Lectureship for the Royal Astronomical Society, and we are very pleased that he will actually give a lecture for our prestigious Heidelberg Joint Astronomical Colloquium today. So welcome, and we are looking forward to your talk.
Thanks, Friedrich. Thanks very much for the invitation. Thanks for hosting me. Thanks for listening to me. Yeah, let me share my slides, and then we can start. So yeah, so my favorite topics are indeed radio pulsars, and they are most easily observed at radio frequencies. And I do observe them indeed in order to test relativistic gravity in particular, but fundamental physics in general. And so that is, to put that in context, we're trying to sit here on our blue planet called Earth, and we're trying to decipher the laws of physics that govern the whole universe from the beginning to the end. And we do this really by just sitting on our planet and receiving, as astronomers, photons or other multi-messenger information like gravitational waves or neutrinos, and really try to understand the world around us. And that's quite a bold thing to do. I like that quote from Richard Feynman, who said, "We don't know what the rules of the game are. All we are allowed to do is to watch the playing. Of course, if you watch long enough, we may eventually catch on a few of the rules, and the rules of the game are what we mean by fundamental physics." And that's really describing what astronomers do, because we sit here really and just watch and try to understand the game. And one of the questions that you can ask, and one of the questions that I'm looking into it, is, for instance, if this astronaut here falls in the same way everywhere in the universe. So around the Earth, like here, or even in strong gravitational fields, like possibly in this scenario. So that's really one of the questions that I would like to answer with our observations and our experiments, where the universe is our laboratory. And the means of doing this is indeed radioastronomy. And I hope I can convince you in the rest of the talk that it's actually a superb tool for probing relativistic gravity or fundamental physics in general. And the reason being is that, let me switch on my pointer. The reason being is this is, of course, the 100-meter radio telescope. It's celebrating its 50th anniversary last month. It's better than ever. It's more productive than ever. And of course, it's a big dish. And because the photons that we receive are usually of low energy, even though they are coming from very extreme and very energetic processes a lot of the times. And so we can see objects that may not be visible at other parts of the electromagnetic spectrum. We can also combine them very easily and build huge telescopes because we get lots and lots of photons that we can easily combine, copy, multiply, interfere with each other, and so on. And so that really allows you to do things that are very difficult or even impossible at other parts of the electromagnetic spectrum. The other thing is radio emission basically propagates through the whole universe more or less undisturbed. So we can really look, for instance, right into the galactic center or literally to the edges of the visible universe. And so that is also quite a nice, unique feature of radio astronomy. And because we can also measure polarization properties of our photons very easily, we can get a lot of information about magnetic fields, for instance, either of the source or in between the source and our telescope. And because we get so many photons, we can really resolve the universe on timescales of down to nanoseconds or so. So we really get a nice dynamic picture of the universe as well. If you want to do that in order to study gravity, you can do this in various ways. And I try to summarize this here in this diagram. Just to put it in context, in the solar system, we encounter weak gravitational fields. And so that's called the weak stationary weak field regime. But again, if you use spacecrafts like Cassini, for instance, you also use radio astronomy technology in order to do your most precise tests. Then, of course, if you go to stronger gravitational fields in a quasi stationary regime, we can do experiments like that Reinhard Genzel is doing with the stars around the galactic center, or you can maybe image the black hole, and I'll talk about that very briefly at the end as well. But pulsars, radio pulsars, are also probing the quasi-stationary strong field regime, but they are also probing radiative properties, as I will show you later on. So pulsars basically probe these two different regimes. And then if you want to go to the very strong dynamical regime, you really have to look at gravitational waves. And of course, we have now LIGO observations, but as I will show you also in this talk, we are on the verge of opening this area also with radio astronomy using pulsars. And of course, on the huge scales, you have the CMB, and again, that's also radio astronomy. So as you can see, it's really a wonderful tool to study relativistic gravity. And so in my talk, I'll try to cover some of these examples. I'll give you first an introduction into pulsar timing, because I will concentrate mostly on those objects. I'll show you how we test gravity, especially with an object that we call the double pulsar. I'll have 2 or 3 slides on relativistic spin precession, because there is a very nice effect that we can use for other purposes as well. And then I'll talk about this galaxy-sized gravitational wave detectors, and I'll talk about black holes towards the end. And then I'll try to put everything in context and give you the general overview. Starting with pulsars, you all know that pulsars are rotating neutron stars. They emit the radio beam along the magnetic axis. The magnetic axis is inclined to the spin axis, and so it acts like a lighthouse. And whenever the beam is pointed in your direction, you see a pulse. And so one pulse period is always connected to the rotational period of the neutron star. The neutron star is, of course, very extreme. It has density inside that we will never be able to create here on Earth. It exceeds the nuclear density by at least an order of magnitude. It has huge magnetic fields of the order of the quantum critical field. So that's 10 to the 9 Tesla or so. And that magnetic field induces electric fields of 10 to the 12 volts on the polar caps. And that's causing an electromagnetic force that exceeds gravity by about 10 to 12 orders of magnitude, even though these are almost black holes. And as I said, the interior of the neutron star is rather bizarre. It's a high temperature superfluid superconductor. And if you want to study really matter under extreme densities, you should do this using observations of pulsars. Pulsars, in particular, for our purposes, are precise clocks. So they cover a huge range of spin periods, 4 orders of magnitude. The slowest rotating pulsar that we know by now has a period of just 23.5 seconds. And the fastest spinning pulsar that we know at the moment has a period of only 1.4 millisecond. And in between, we have, for instance, the Wheeler pulsar with 89 millisecond and the Kramer pulsar, which is maybe the most famous pulsar, with a period of only 33 milliseconds. And as an radio astronomer, it's very difficult to show you a picture of a neutron star or pulsar, but at least we have the advantage of make them visible. And I don't know if you can hear this. Oops, wait a second. I had to do this from another computer. That is the Wheeler pulsar, 89 milliseconds. That is the sound of the Kramer pulsar, which rotates 3 times faster. And for a millisecond pulsar, you can basically only hear a constant tone of about 700 hertz in this case. And that sounds remarkable, but the physics is even more remarkable. For instance, if you think about this, the slowest rotating pulsar has a period of only manages only 3 rotations per minute. If you compare this with a washing machine in a fast spinning mode, maybe that washing machine does 1600 rotations per minute. That looks already quite fast. If you have a fancy car, that engine may do 20,000 rotations per minute, but it's really nothing compared to what nature provides us, whether we have an object that has as big as a city, 20 kilometers across or so, which rotates more than 40,000 times a minute. So if you think about this, this means that the speed at the equator is a significant fraction of the speed of light. And the fact that it doesn't pull apart, that it doesn't fly apart, means that the gravitational acceleration must be huge. And indeed, if you would have a test mass and you let this drop from 1 meter height on a neutron star, then after 1 microsecond, it would already have a speed of 8 million kilometers an hour. And for us, however, for the experiments I'm talking about in the following, you just need to know that it's just a massive flywheel in space. It stores a lot of rotational energy, and therefore it's very difficult to disturb the rotation, and that makes them really stable clocks. So what we did, one thing that we do with them, for instance, if they happen to be in orbit around a common center of mass as a companion, then sometimes this pulsar, which I mark here in red, is sometimes further away and sometimes closer. And so the signal that you receive with your telescope is sometimes coming too early and sometimes coming too late, depending on the distance. And that's the path length difference we can measure to a precision of about 30 meters. So we can position the pulsar to about 30 meters in its orbit, regardless of how far away the orbit is from Earth. And we do this with an experiment called Pulsar Timing, where we basically just measure the arrival times of the pulse on Earth and compare this with some prediction. So the way it works is we have a pulsar, which is then received by our radio telescope. And typically the pulsar signal is too weak and buried in the noise. So we fold the data with the pulse periods to reduce the noise and increase the signal. And eventually we measure the time of arrival, the TOA. And then you have a model of how the pulsar sort of rotates and how it moves, and you predict the arrival time into the future. And then you repeat the experiment sometimes later, and then you compare basically the difference between the expected arrival time and the measured arrival time, and it gives you a residual. And if your model is perfect, then you would expect basically random the residuals around 0. But if you see systematic variations in your residual, then there is a physical effect that you have not yet modeled. And then you take this into account, and that's how you measure all these different things. And what we do really is we count the rotations between 2 observations. I can go back to the telescope 30 years later and it may have done tens of billions of rotation, and I can tell you plus minus 0 how many rotations this pulsar has done. And so this method is about a million times more precise than just measuring Doppler periods. And that is a bit of a show-off slide that kind of gives you the impression of how accurate we can actually measure things. So for instance, the one pulsar here has this spin period at a given time, and we can measure this with 3 attoseconds. The number in the brackets is the uncertainty in the number before. So we can measure this with 3 attoseconds accuracy. That's 10 to the minus 18 seconds. Or we can measure periods of binary pulsars, for instance, to nanoseconds, even though the orbit is a few hours, and measure sizes of the orbit, eccentricities, masses, and so on. So you can already see that we have indeed a very good precision to do physics. And I'll talk about this gravitational wave detection a little bit later on. Right, so talking about relativistic gravity, the first time we could use pulsars to actually test gravity, of course, came with the discovery of the famous Hulse-Taylor pulsar by Joe Taylor and Russell Hulse, who discovered using the receiver telescope, which has now collapsed, unfortunately. But they used that telescope to discover this pulsar, which has a 59 millisecond pulsar in orbit around an unseen second Newton star in less than 8 hours. It was a highly eccentric orbit, as you can see also from the radial velocity curve. And by observing that, they basically showed in the years after that first of all, gravitational waves exist as predicted by general relativity. And this is the sort of the proof of that. That's an updated version of Joel Weisberg, who really did a lot of work on that system, may have deserved also the Nobel Prize, I think in addition to Hulse and Taylor. And what is plotted here is basically the shift of periastron as a function of time. So what means that as the pulsar, let me start that animation again, as the pulsar is rotating around its companion, the system creates gravitational waves. The gravitational waves carry away energy, and as a result, the orbit shrinks. In this case, in 300 million years, the orbit is so compact that the Newton star merges, and you see this double Newton star merger event that LIGO has picked up. And that's so with time, the periastron, the time of closest approach, arrives earlier and earlier and earlier as a function of time. And these are the measurement points of Taylor and collaborators. And these are the and the red curve is the prediction by general relativity. And as you can see, it's like pearls on a string. In 1993, the deviation from zero damping was basically large enough for the Nobel Prize Committee to give them the Nobel Prize in physics. So that was the first evidence for the existence of gravitational waves, and a few other things you could show with that system. That system used to be the most suitable system until 2003, and then when we discovered the double pulsar. And here is already a result of the double pulsar. I go back, explain it in more detail later on. But what we actually measure when we observe a pulsar is so-called binary pulsar, so-called post-Keplerian-Parameters. These are theory-independent strong field analogs, if you're familiar with the PPN formalism. But for you to know just right now, if you're not familiar with that, they're basically corrections to the Newtonian description of the orbit, but in a theory-independent way. To give you an example, Mercury, for instance, precesses in its orbit, and binary pulsars do this as well. And so you have, for instance, an omega dot, a change of the periastron angle as a function of time. This is given by this quantity here. Or the orbit shrinks because of the loss of energy due to gravitational waves, and therefore the orbital period decreases, and so on. So, and in what is wonderful about these formalism here is, as shown by Damour and Taylor, is that each of these so-called post-Keplerian parameters can be written as a function of the Keplerian parameters, mostly the orbital period and the eccentricity, and the unknown masses of the pulsar and its companion. And these are and each different theory of gravity gives you different functions, different combination of how you combine the keplerian-Parameters and the masses. So these are the equations for general relativity to the leading order. And so in principle, you have several quantities if you measured more than two, and you have two unknowns, the masses of the pulsar and the companion. And so you solve this and plot these curves in the mass-mass diagram, as we call it, the pulsar mass on this axis, the companion mass on this axis. And then each measurement gives you a line in this diagram. But you have sort of many equations, but only two unknowns. So if the system is described properly by your theory of gravity, these curves should all intersect in the same pair of masses. And this is indeed the plot for the double pulsar. We just submitted it a couple of weeks ago. And as you can see, they nicely intersect in just a single point, and I explain you the different effects on the next slides. So the double pulsar is an old 22 millisecond pulsar in an orbit with a young 2.77 second pulsar. And the orbit is quite compact, only 147 minutes. And it's slightly eccentric. And the nice thing about it is we see it actually from edge on. So this is going here into the right orbital configuration. So this is actually the orbital configuration that we see the system on. It leads to eclipses in the system, which I won't talk about today, and a lot of other interesting relativistic effects that are listed here. I will not talk about orbital precession and gravitational redshift because you know them quite well, I think, from the solar system and from Mercury, and you can do this even in the lab. I'll tell you a little bit about the other effects that we see in the system. In particular, we found a few new ones like aberrational light bending and orbital deformation. So I'll tell you a little bit about that. But let me start again with the gravitational wave damping. This system is also losing energy due to the emission of gravitational waves. And that leads to an increase in the pulse period, in the orbital period of 107 0.820 picosecond a day. So this means that these pulsars approach each other every day by 7 millimeter. And that means that in 85 million years, they produce that kind of merger that LIGO has observed a few years ago. The precision will actually improve with time, the more orbits we observe. So unlike in a gravitational wave detector, we just merge it and that's it. We can continue to observe this pulsar, and we have done this in this case for about 18 years now. And so this is the same plot I showed you for the Hals-Taylor pulsar. This is for the double pulsar. And again, the red curve is the prediction by general relativity, and the blue points are our data points. And you see that here the residuals, the deviation from the prediction. You can see this is, again, a beautiful confirmation of the prediction of GR, and we submitted this about 2 weeks ago. And so this is the most precise test of GR's description of gravitational waves. And it's more than 20 times better than what's possible with the Hals-Taylor pulsar, and order of magnitude better than what you can do with LIGO right now. In fact, the precision is so high that we need to take the mass loss of the pulsar into account, because the pulsar rotates, it loses rotational energy, and because E is equal to mc square, that means the pulsar is losing about 6.7 billion tons a second, which seems to be a lot, but in terms of its actual mass, it's a tiny, tiny fraction of its Newton star mass per second, but we can actually have to take that into account because it means that the orbit is also losing mass. And so this is including in the calculation here. And the agreement is very nice. We also see light propagation in strong gravitational fields. That's things you can't really do, for instance, with LIGO. Here, what happens is that because we see the pulsar from edge on, the signal has to propagate through the curved space-time near the companion on the way to Earth. And that means this extra path length takes a little bit longer. And so that means that the pulse arrives a little late compared to the expected arrival time. So if that's the deviation from the expected arrival time, you see that the pulse arrives progressively late and then gets back to normal time. and the peak is exactly at superior conjunction when pulsar A, as we call it, and pulsar B are lined up in line to the observer on Earth. And again, the blue points are our measurements, and the red curve is the prediction by general relativity. And again, comparing the observed to the expected value, this is a rather precise test of general relativity. In fact, you get two tests, one gives you the shape and one gives you the amplitude, and that gives you two independent post-Keplerian-Parameters. Now, actually, that looks like a perfect agreement, but in fact, it's not. There's another effect that you have to take into account. So if I zoom into this and subtract the red curve, you can actually see that there is an interesting systematic signature in this plot. So, so we're zooming in here. So as we come to superior conjunction, suddenly the pulse arrives a little late. And that superior conjunction, it changes, the residual changes sign, then the pulse comes a little early in order to actually get back to the expected arrival time. And so we were puzzling for half a day or so until we discovered that. The reason is actually a combination of two effects. First of all, we discovered that the speed of light is finite, because in our previous description in a timing model, we basically didn't take into account that the photon, when it leaves pulsar A and moves towards B, by the time it actually reaches pulsar B, that pulsar has moved quite a bit because it's a compact orbit. And so this leads actually to a small shift in the Shapiro delay curve. But that's not all. We also figured out that the pulsar the pulsar signal undergoes light bending, because the curvature of space-time here makes the light to deviate from a straight path, and therefore the pulsar has to shoot its light before superior conjunction slightly late in order to compensate for this bending here in order to arrive on Earth. And after superior conjunction, the pulsar has to shoot its light a little early to compensate from the bending in the opposite direction, and hence you get a signature which is positive and negative, depending actually what the spin direction of the pulsar is. So this signature tells you the direction of the spin of the pulsar relative to your orbital angular momentum vector, and it turns out to be prograde, which you would expect it actually from formation theory of the system. And in fact, the distance, the pulsar signal without this bending delay would pass the companion in 10,000 kilometer distance, but because of this actual bending, it is actually slightly more, 10,600 kilometers, pretty close. Anyway, if you compare the prediction of GR again with the measurements, you see that within 1 sigma, it's basically consistent. So, I think it's 1.2 something sigma deviation. So I think we call that being consistent with GR. So that was a new effect that we had never seen before. It was predicted, but we didn't quite expect to have the precision to actually see this light bending for the first time. The other effect that we need to take into account for the first time is the Lense-Thirring effect, frame dragging. So what happens is that if the pulsar spins, it directs the space-time with it. And this has been shown with gravity prop B and the gravitomagnetic field of the Earth. But here we can actually test it, or not test it yet, but we have to take it into account for strong gravitational fields. And in fact, it adds on to this periastron advance. So we have this orbit precessing in space. It's like Mercury, which has this 42 arc seconds per century extra precession. Here in the double pulsar, this makes 17 degrees per year rather than 42 arc seconds per century. So we have this change of omega of the angle of periastron. We describe this with omega dot, as I mentioned earlier. And in addition, we have to take into account this frame dragging effect because it contributes to the observed value of omega dot. So we have the contribution of the normal precession at first and second post-Newtonian level. And then there's a contribution which of the same order at the first post-Newtonian level that comes from frame dragging. And so what you need to know now is that this contribution that comes from frame dragging actually contains the moment of inertia of the Newton star of pulsar A. So if we can isolate this contribution relative to the other orbital precession contributions, then we can actually measure the moment of inertia of the Newton star, in this case from pulsar timing, for the first time. We're not quite there yet, but we have to take this already into account. And we get an upper limit of the radius of the Newton star of 22 kilometers at 90% confidence limit, just based on pulsar timing. And this is the PDF on the moment of inertia. So this is this nice work by Dietrich et al. Of course, it's consistent, but it actually peaks, our PDF peaks away from 0. And hopefully with more measurements, and we have some paper out there where you can see how fast that will go. We'll be able to actually measure very independently, just on pulsar timing, the moment of inertia in a number of years. And so that is the first time, again, that we can do this with pulsar timing alone, just getting a limit, for instance, on the size of the Newton star. One strange effect that we also see for the first time is, well, actually not for the first time, the Hals-Taylor pulsar had indication of that earlier, that the orbit in the relativistic binary system is actually not an ellipse, but it's slightly deformed. I will not go into the reasons why that is the case. But the elliptical orbit that you would expect is here in red, and this is highly exaggerated. But what we have measured, because we can see it's deviating from 0, is that it is slightly deformed like an egg. And this is the prediction of GR, and this is our measurement right now. We certainly need more data to make this a much more significant measurement. But again, if you don't take it into account, you see some apparent deviations from GR, which actually there aren't. It's just if you ignore this effect, you get this correlation and you see some apparent deviation. But everything is fine. GR passes this also very nicely. Yeah, then I come back to this sort of strange diagram where you put in all these constraints. So this is the orbital precession. This is the decay of the orbit. These are S and R, your Bohr-Shapiro delay parameters. And this particular line here is the gravitational redshift, which I haven't talked about. It just means that the pulsar clock goes slower when it's closer to its companion, hence deeper in a gravitational field. And this one here, this is because we have two visible pulsars where we can measure the two orbits independently around the common center of mass, and it gives you the mass ratio. And as you can see, everything agrees very nicely and intersects in a single point. We also have seen relativistic spin precession in this pulsar. There was a different work, and we're working on improving this big error bar here. But again, that's also consistent. And if you want to summarize this, these are the relativistic effects that we have seen, many more than in any other system before. Here, that's how you derive the masses, because this is just the intersection point. This is the precision that we have. And this is the measured sort of parameter. And this is the comparison of the observed and the expected values expected in GR. And you can see that having the error, the number here gives you again the uncertainty in that number. And as you can see, everything is nicely consistent with the prediction of general relativity. We can test also alternative theories of gravity. That would be another talk. So I'll restrict this thing to general relativity here. But in principle, you can also test alternative theories of gravity and show that some of them don't agree with the data, like relativistic bond, for instance. One or two slides on some interesting effects, which is also relativistic spin precession, like we've seen in a double pulsar, but this is the best test case for this right now. What happens here is that we have a pulsar, that's the phone number, that is oriented such that we see both the North Pole and the South Pole of the pulsar, at least we used to. So what happens is that the spin axis of the pulsar is slightly misaligned with the orbital angular momentum vector, and as the pulsar precesses due to spin orbit coupling, the way our line of sight cuts the emission beam changes. So this is the North Pole, this is the South Pole, And this is the red curve here, by the way, is linear polarization. So this is more or less 100% linearly polarized. This emission is a circular polarization. You can see then measure what the position angle, so the orientation of your E vector in your radio light is. And you see it's systematic, it's not random. It actually has a swing that goes under the main pulse or north pole, and then goes in the opposite direction under the over the other pole. And we understand this in a geometrical way. Let's assume this is your cone of your pulse that sweeps over your telescope. This is the magnetic axis, and this is how your line of sight cuts this emission beam, and that produces this pulse here. As we are, as the light is polarized, what we actually measure as the position angle here is basically the projection of the magnetic axis, of the magnetic field direction on your line of sight, because the plasma is like pearls on the strings moving in this very strong magnetic field along the magnetic field lines. And we also assume that the polarization is directed exactly in the direction of the magnetic field lines. And if you change your line of sight, you cross it under different directions, and hence you see this S-like variation of your position angle, just as you can basically see in the observations. For the opposite pole, for the south pole, we cross the magnetic pole on the other side, and hence the corresponding position angle has the opposite swing. Now what happens is, because of this precession, our line of sight moves out of the main pulse, or its north pole, and into the south pole towards the magnetic pole. What happened is then that when we observed this pulsar for more than 10 years, this pole becomes invisible because our line of sight moves out of the beam, while this pole becomes stronger as you move further in. And that's shown on this diagram here. And not only the position angle also changes from this swing on this side as we approach the magnetic pole, which is here. Suddenly we become flat and changes the direction, as you would expect it from this nice simple geometrical model. And this is not only the first time that we could verify that this swing actually comes from this geometrical effect, because as we cross the pole, it changes the sense of orientation. But more importantly, we can use this also to measure the rate of precession of the pulsar spin around the angular momentum vector. And we measure 2.17 plus minus 0.11 degree per year. And that's exactly consistent with what general relativity predicts. So this is another test of GR that we can use not via pulsar timing, but using the emission properties. And we actually use this for the first time to map out the beam of the pulsar in very, very much great detail, more than we could do in any other pulsar before. And we published this about 2 years ago. Right, let's change topic a little bit, and I come back to gravitational wave detection. So for the last 5-10 minutes, I'll go through this, and then I'll wrap up. So the LIGO, of course, you know, measures gravitational waves as the gravitational wave passes through the detector, which is a Michelson interferometer. So you have a laser beam that you use to basically measure the relative change in length of the detector as the laser beam bounces back from the mirrors and becomes interfered in the center again. We can upscale this to the size of the galaxy by using pulsars as our signals, and use the Earth to compare the propagation time, the path length differences as the gravitational wave passes over this pulsar Earth system. So pulsars that are given in one direction, there will always be coming too late, too early, too late, too early in the residuals, and those separated by 90 degrees because we have quadrupolar gravitational waves will be anti-correlated, just like here in LIGO. When this one is squeezes, this one is stretched, this one is stretched, this one is squeezed. And so we see the same thing also on galactic scale. So if you compare the arrival times between pulsars on the sky, you would expect a correlation, which is given by the so-called Helling and down curves. Again, pulsars in the same direction or 180 degrees apart show a positive correlation, so they're trying to be in sync, late, early. And pulsars that are separated about 90 degrees, they are late, late, anti-correlated. And so that's how you would detect gravitational waves. And we do this experiment in a frequency regime that is in a nanohertz gravitational wave regime, which is nicely complementary to the regime of LISA, which is at micro or millihertz, LIGO at kilohertz, and the CMB at very low frequencies. So that's where the pulsar timing array, as we call this experiment, is located. And the signals that we expect to find are actually coming from galaxy mergers. We, of course, believe that the bigger galaxies today were results of mergers of smaller galaxies. And whenever that happens, and here's some nice simulations compared with pictures from the Hubble Space Telescope to show you that this is actually still happening. And so if you have this merger of these two galaxies, then in the center of these galaxies, you have this supermassive black holes, which eventually form a binary system. And then they have orbits of a few years. And so that's exactly the nanohertz regime that we will expect to see with our pulsar timing array experiments. So we have done this experiment in Europe now started about 25 years ago. And I think we are about on the verge to detecting something, but we are not alone. We do this experiment in Europe. We have the Lovell telescope in England, the Westerbork telescope in the Netherlands, the Nancy telescope in France, and the Sardinia telescope on Sardinia, and of course Effelsberg. But we also sort of in competition with our American colleagues and our Australian colleagues, but actually we also work with them in the international pulsar timing array, where we try to combine the data from all the telescopes. And you may have seen the news, Nanograph was first to release it. We have seen it also for a while, but we're a little bit more cautious. There is something what we call the common red noise process. And this could be the first hint of gravitational waves, but there may be other sources why we have a correlated noise. We haven't seen this Helling and downs curve yet. And so we should check other possible correlated noise sources. And we're doing this right now. And of course, more sensitivity would help. And so we are also now enlisting the help of the MeerKAT telescope in South Africa, the GMRT in India, and the Big Fast telescope in China. And indeed, they will provide a lot more sensitivity. FAST is twice as big as Arecibo. So this is a nice picture. This is the MeerKAT telescope, where we basically have the core of the square kilometer array already operating for a few years now. So these are 64 dishes. And in Europe, we basically once a month combine our big dishes to a 200-meter equivalent dish that we call LEAP, the Large European Array for Pulsars. That was actually constructed, so to speak, by an advanced ESC grant that I had. And we do this more or less now for 10 years, once a month. And that really scales this signal to become equivalent to a 200-meter dish. Just a few words about MeerKAT. We actually, in our institute, providing 64 receivers for that telescope at so-called S-band. That's 1.7 to 3.5 gigahertz. This is one of the receivers on a telescope. And then we use the telescope and the receivers to actually pixelize the whole sky to search for pulsars. And I won't go into details, but maybe just want to know that we basically write 3 petabytes a day. So it's a lot of data. We need to do machine learning and all that fancy stuff to actually analyze the data before we have to delete them and to continue with the observations, because we can't store the data. So that's a taste of what the SKA will give you. And again, we find lots of pulsars already, and this is the first binary, relativistic binary we probably discovered just in the Galactic Plane survey that was done by our own institute in compensation for the receivers that we delivered. So stay tuned, there's much more to come, but it's just a teaser that is some very interesting results coming up. We also have some new pulsars in the small imaginary clouds, but again, that's a different talk. I want to finish up with a few words about black holes. And of course, what we're still trying to find, also hoping that, of course, MeerKAT will turn this up, is a pulsar around a black hole. Because then all these effects that I've showed you for the double pulsar would be scaled up enormously. And actually, if you have a more massive black holes, these effects scale with the square or the cube of the masses, and that would then make easily measurable frame dragging and even the quadrupole moment of the black hole. And that would allow you to test the Noether theorem, which means that the black hole is a very simple object, just determined by the mass and the spin, and every other thing like quadrupole moment would be determined by these two quantities. Ideally, you would like to have a supermassive black hole, let's say 4 million solar mass, then you can really measure the Noether theorem to 1% precision. Why do I take 4 million solar mass? Because we know one black hole, which is of course that one in the Galactic Centre, Sagittarius A star. And this is one of the nice observations of Reinhard Genzel and his group, where they, of course, rightly were awarded with the Nobel Prize with Andrea Ghez to show that there is such a black hole in the center. And so this would be the really cool place to find pulsars, and then we can actually probe the pulsars in the same way as we've done with the other Newton stars, probe the black hole properties of Sagittarius A star. So I've been searching for pulsars for quite a while, and the closest we have got to the known to do a Sagittarius A star was with the Effelsberg discovery of the Galactic Centre magnetar. It's not quite close enough. We need something closer, and so we're trying to keep searching. We would like to combine this actually with the upcoming picture of Sagittarius A star that we're doing with the Event Horizon Telescope, where we use radioastronomy to basically get the shadow of a black hole. And I'm sure you have seen this all many times before by now. But the idea is that if you have the black hole embedded in this hot accretion disk, some of the photons will just not make it to the observer, and they will be either on infinite loops around the black hole or fall into it. And so you have a paucity of photons that will make up your black hole shadow. And of course, we have done that for M87, presented this a couple of years ago. And that was a nice experiment. But I think when people tried to sell you this as a gravity test, it wasn't quite that yet, because actually the picture of the black hole will depend on the masses, on the orientation of the accretion disk, and on the distance. And for M87, we didn't know that value is very good enough. But this is, of course, different for Sagittarius A star, where we have all this other wonderful information. And I refer to this work. I won't go into detail how we can actually combine the pulsar constraints. If we find a pulsar in the shadow and the stars of Genzel and collaborators to combine information to make this a gravity test. And this was, of course, the focus of our Black Hole Chem Synergy grant that was just finished. And that was, of course, a major stakeholder in the Event Horizon Telescope, where we're very careful in pointing out that we haven't actually made a GR test. They said it's consistent with the expectation, but we were clear that if you think about it, the quality of the image does not allow you yet to distinguish between a Kerr or gravity GR black hole and that of an alternative theory of gravity. And we didn't know the mass of the M87 black hole in advance. There were two estimates, stellar or gas black hole masses. Happened to be the stellar mass black hole because the stellar mass estimated black hole, because otherwise the shadow would not have been visible. But of course, if you find a pulsar in Sagittarius, around Sagittarius A star, with all the prior information and the imaging, this is of course a completely different story, and that is still work in progress. And wait and see what happens at the end of this year. Just as a comment, if M87 had a companion as a black hole, it would produce gravitational waves that we will actually easily pick up with our gravitational wave pulsar timing array detector. We haven't picked it up. We can give you a very stringent upper limit on M87, so there is no companion to the M87 black hole, but we know this now from the image as well. So finishing, kind of putting everything together is trying to be done in this diagram where I plot the curvature, maximum curvature of space-time in a system versus the gravitational potential. And you can see that, of course, the gravitational wave detector signals appear in the most extreme top corner, right corner of the diagram, but actually the pulsar experiments are pretty close by. So we are also probing the strongest curvature, which is orders of magnitude more curved than the space-time around M87, for instance. There are the solar system tests. There's the nice stars from against and gas. And this will be the position of when we publish the Event Horizon Telescope image of Sagittarius A star. Just to finish up and come back to my initial slide about the astronaut, we have done this experiment, whether the astronaut falls in the same way around strong gravitational fields, recently using a so-called triple system. Here we have a pulsar and a white dwarf, and they orbit each other. And then they will also move in the gravitational potential of an outer white dwarf. So this system has an orbital period of about a day, and the outer white dwarf has an orbital period of about 1 year. And so we can actually test if the system falls independently of the composition of the white dwarf or the neutron star in the external gravitational field of the second white dwarf. And this is what we published in last year. We put the best constraint on the universality of free fall or the violation of the strong equivalence principle in any strong gravitational field. And indeed, it's again, GR passes this test again with flying colors. I won't bore you with the summary of what I've just described, but maybe just saying that I think it's quite ironic and sad that Einstein hasn't lived to see the discovery of pulsars and actually most of radioastronomy. All the tests we've been done are using methods that he didn't even know, and yet his theory has this predictive power to actually predict all the outcomes of our experiments so far, so well. And I think that is truly remarkable. So my final famous last words are from Albert Einstein's letter to Arnold Sommerfeld, when he used the peristron messages of measurements of Mercury to basically verify as a first test of GR that his theory predicts the right peristron advance of 42 arc seconds per century. And he said, "There comes the pedantic precision of astronomy to the rescue, which I have ridiculed silently so often in the past." And if he were impressed by the Mercury peristron precision measurements that were available at the time, I would like to think that he also would have liked the precision of our experiments. And that's all I wanted to say. Thank you very much. Thanks for your patience.
Thank you so much, Michael. That was a truly fascinating snapshot of that field. I for one, was very, very impressed with not just the GR and the precision, but all the other interesting things which you seem to be able to find out. And I'm sure there's lots of questions following on from this. We have about 5 minutes before we start our extended question and answer session following the main colloquium. So I invite people to put their hands up and if also type questions into the chat if that's easier. So just see who's there. Okay, Nadine Neumeyer has a question.
Hi, Michael. That was really an excellent talk, and I learned a lot. So thank you very much. So I had a question about what was used to be called the missing pulsar problem, and I think it's around Sag star that we are seeing fewer pulsars that we expect to see. And I never really understood that problem. So maybe you are the right person to ask, what is causing this, and why do we see fewer pulsars than we would expect?
If I knew the answer, I would have found it all. No, very good question. So if you think about the population of neutron stars, we have all the signs of massive star formation in the galactic center. We see supernova remnants, we see X-ray sources, we see Wolf-Rayet stars, the progenitors. So there should be a lot of pulsars there. And yet, indeed, apart from the 5 pulsars I showed you on this MeerKAT overview lay, these are all the pulsars we know within a few degrees of the galactic center. So where is the rest? There are some modeling that predict there should be maybe up to 1,000 pulsars in the inner parsec. And that's why we are so keen to find them, because just a single one would be sufficient to measure out the properties of Sagittarius A star. And yet we haven't found them. The closest we found was this galactic center magnetar. So there's various theories about it. Some people say, like Dexter, for instance, Jason Dexter, he proposes that you can only find magnetars in the galactic center because for some reason, maybe they all turn magnetar and not becoming normal pulsars. I'm not quite sure that is the final answer. I think MPIR number, first of all, the galactic center is quite hot, even in the radio. So the sensitivity is always reduced. And so far, we had never had a big collecting area big enough to search at high elevation. So we always had also the ground, the spillover from the ground radiation. So with Effelsberg, we're just grazing the horizon, for instance, and GBT is not much better. So with MeerKAT, for instance, we will have for the first time the galactic center really overhead with some very nice sensitivity. And that's why we try to use also MeerKAT to search for pulsars in the galactic center. If it's not a sensitivity issue, it could be the interstellar medium, because interstellar medium is very turbulent, it's inhomogeneous, and it produces scattering. So basically, you have multipath propagation, and that smears out your pulse. And you cannot correct this with any instrumental means. It's just there. The only chance is to go to high frequencies. So what we have done, we used actually ALMA and picovelator to search for pulsars at very high frequencies to kill that scattering effect. But then pulsars become weak because they have a steep spectrum. So it's like the perfect storm. You want to go to high frequencies to beat the scattering, then the pulsars become weak. And maybe you don't, and flat spectrum sources are rare in pulsars. So it's to find the sweet spot where pulsars should be visible is yet missing. And so we're trying every possible combination, high frequency, low frequencies, big telescopes, staring at it. So the hope is, my expectation is we'll find those pulsars eventually. It could be that they're all millisecond pulsars because they can easily capture a companion, accrete mass, and then spin up. And then the scattering effect is much, much more severe because the pulse period is much more easily smeared when it's short. So, and then you have to go to high frequencies. So my dream configuration would be ALMA band 1. I think that would have a really good shot in finding millisecond pulsars in the galactic center.
Okay, thank you very much. Thank you.
Okay, any more questions? Yes, Georg Volshin. Go ahead. Georg?
Yes. Thank you very much, Michael. My question is about the determination of spin, which is, of course, straightforward in case of your wonderful pulsars. But how is it in case of merging black holes? Do you meanwhile have an accurate method to determine the spin from the LIGO signals?
No, the signal to noise and the LIGO signal is not good enough to do this. Eventually, if you have LISA, for instance, shouldn't be a problem. But the signal to noise for the mergers that we have seen so far and the ring down is not sufficient to measure the spin. That's why actually finding a pulsar around a black hole would be so nice, because via relativistic spin orbit coupling, you could actually figure it out. In fact, we can show that for a pulsar in Sagittarius A star, even a normal pulsar, you can get the 3D orientation plus the magnitude of the spin of the black hole. But first, we have to find that pulsar in the galactic center, which is, as you just heard, very difficult.
So chances are slim to actually determine this.
once we find a pulsar in the right orbit, I think the chances are very good. But it's this overcoming this hurdle, finding the pulsar in the first place. Once you know that the pulsar is there, it's actually much easier to observe, because once you know that, you can basically fold the data. But finding the pulsar in the noise, it's much more difficult than folding the data and timing it. So that is the goal of pulsar astronomy. And Galactic Centre is still a good place, but we can also look at globular clusters, because there you have also lots of exchange interactions, and then you may find a stellar mass pulsar black hole system there. And so that's why you're also looking at globular clusters.
Thanks a lot.
You're welcome.
Okay, well, I think we'll postpone further questions to the session after the colloquium. Before we thank Michael, I'd just like to make an announcement about next week's colloquium. So I'll just take the screen here. So that's we're going to be welcoming Peter van Dokkum, who's going to be talking about something which couldn't be more a contrast, going right to the very most diffuse objects in the universe, but nevertheless he's going to tell us, I think, something about fundamental physics, possibly in particular dark matter and even gravity, even from these observations. So there is a connection, and that's next week at the same time. So now I'd just like to ask everybody if they would open their videos and open their audios, and let's thank Michael for this truly amazing vision of the present and the future in radio astronomy. Thank you, Michael.